The 1.68 is, my standing wave is going to be in the length of the tube. So I measured that length, and it was 84 centimeters. The first harmonic is a half of a wave. Therefore, the wavelength, since that's half a wave, the wavelength would be twice as big. That did not sound like a convincing.
So just 84 times 2 to
Yeah.
get the whole.
Maybe you could just 84 times 2.
Oh,
Just,
okay.
yeah, so-
Oh, that's what you're. Oh, sorry. Half of a wave is equal to 0.84, then multiply both sides by 2. All right, so 202.38. That's the first harmonic, if we predicted correctly. All right, so here we go. We nailed that perfectly. That's incredible. All right, so what's happening here, why you can't hear anything, as I swing the end around, this end obviously moving a lot faster than this end. Because this end is moving faster, there's a decrease in pressure on this end of the tube. There's less air pressure here than there is here as this swings around. Because there's less air pressure here, air gets sucked up through the tube. And the ribs there help the vibration. You could still do it if it were a straight tube, it just wouldn't be as musical. So that's actually the second harmonic, because the first harmonic I can't swing slowly enough to suck enough air through it to get the sound. So, the second harmonic. The second harmonic is one wavelength. So I have one wavelength is equal to 0.84 meters. I will do this math for you. Shocking. And so the math here, my wavelength has changed, so the frequency is going to change. This is 0.84 meters. And this will be 404.76 hertz.
So how did you go from half the wavelength equaling one wavelength?
Because the first harmonic is a half of a wave. The second harmonic is a full wave. The next harmonic is 3 halves. We add a half every single time. So so the first harmonic we don't actually hear. That's the second harmonic. So we're going to predict that sound. Third, fourth, and then fifth if I swing faster. You want to ask it again? Because I don't think I answered your question.
Well, I'm just wondering how the half wavelength equals to one wavelength when right under the half, you have 1.8.
All right, so the first time we did it, we were looking at the first harmonic. And the first harmonic's a half a wave, so that's why I had half of a wave there. The second harmonic, which is the one that we're predicting now, is one wavelength.
So then the next one would be 1.5 equals.
Yes. Yep. Is there another question? Or same question?
You got the 404.76 from the 3 or 4 meters per second equals F times 0.84, right?
Yes.
Okay.
And I knew it had to be roughly twice what the last one was, because we cut the wavelength in half.
So, wait, why is it not 1.68 meters then for the?
Because in the second harmonic, we have an antinode at each end, and then we have a node roughly here and here, and then another antinode in the middle. So for the second harmonic, that's one full wavelength, is that long. For the first harmonic, the first time we did it, that's a half a wave. So the full wave would have to be twice as long. As we go to the increased harmonics, the wavelength gets smaller. So for the second harmonic, that's roughly the wavelength. For the third harmonic, that's gonna be somewhere around there.
Oh, okay.
That's the harmonic. That's the wavelength. And then fourth harmonic, fifth harmonic.
Yeah, that makes sense.
Okay.
A little bit more. A little bit more.
That makes sense a little bit more, or do you want me to say a little bit more?
Yeah, it makes sense a little bit more.
Okay. Riley?
So the numbers we're getting for the frequency, depending on how the measurement changes, we're just measuring the frequency for that part of the wavelength?
We are measuring
Or,
we measured the length of the tube, and then based upon our knowledge of physics and standing waves and harmonics, predicting, saying how many wavelengths there are for that harmonic. And then based on the length of the tube and how many waves it is for that harmonic, we're figuring out what the wavelength is.
So the only thing that changes is the harmonic.
So we need to know which harmonic,
And the length stays the same.
yes,
Okay.
yeah. Now, if you wanna make an argument that I'm gonna swing it faster for the other harmonics, it's gonna stretch a little bit more, probably. Good enough for what we're doing right now, just assuming that the length actually is one length. It's relatively solid. I can stretch it, but not too terribly much. Other questions?
So we're working with the second harmonic?
Yes, first harmonic, we can't hear. The next harmonic, I think we will get somewhat close. It depends upon the mood of the universe. Or 4.76. That sounds like about 404, right? What? Now, one thing that I have to deal with here for my own hearing is that there are two different materials. This is a plastic tube swinging through the air, and the speaker is something vibrating back and forth. They're different materials, different timbre. Anyone done music? Is it timbre or timbre? We'll go with timbre. A different timbre because of the material. So we need potentially some better way of doing it. Now, I heard them the same, but I want to hear them or close to the same. But I want to hear them close to the same. But if I play them at the same time, we should get that the constructive, destructive interference that we heard the other day. The beats, as it is, doesn't work. There's a little extra trill there. That trill is indicating that we are close, not dead on, but we are close. So not hearing the same trill that I heard before, and I'm trusting all of your hearing is better than mine. Did you hear the trill? I got a couple of nods, a couple of blank stares. We'll assume the blank stares were nods. All right, let's go to the next harmonic, which is easier to produce on the tube. The next harmonic, the length is still going to be the same. It's still 0.84 meters. And this time it's 1.5 wavelengths. 0.56. So now that my wavelength has changed to 0.56 meters, 607.42, 14. Not as close as the last one. Okay. Well, hopefully there was enough evidence to support some of what I'm saying. That one, I didn't hear the trill on that one. So, oh well. It's a physics demonstration. You know, after coming in with the incredible results of last time when we did the third harmonic with the water tube, I think we used it all up then. Questions to hear? And the last topic I actually want to hit, if I can figure out how to do this, because otherwise you're going to be left with my drawings, which isn't pretty. Oh, wait a second. Can I do browser. Hush. Okay. Thanks for giving me an option. Screen share. What screen will it share? All right, so I don't have a camera anymore that will display. Oh wait, turn on Windows. No, that's not what I want. I don't suppose anyone knows how to get this onto there. Well, you're left with my drawings. All right, so imagine that I've got a very still pond and I throw a rock into it. And the rock hits the water. What's going to happen after the rock hits the water?
There's a ripple.
Yep. And so a little bit of time later, there's going to be a ripple there, and then that ripple gets bigger as it expands. Now, after a certain amount of time, I throw a second rock and I hit in the exact same spot as I did before, because I'm that good. And so I'm going to get a second ripple. And then sometime later, I'm going to throw another rock and hit indeed the exact same spot. And that ripple will get bigger. So I got these three ripples that are expanding outwards. In terms of waves, these are surface waves. The wave distance from here to here is the wavelength. And the time it takes from the first rock to the next rock to the next rock, that's the period. So, any questions on what this drawing represents? These 4 moments in time. All right. Now I'm going to run through the same scenario again, change it slightly. So I throw a rock into the water and I get a ripple coming out, which gets bigger and bigger and bigger. Then I throw my second rock, except this time I'm not throwing it in the exact same spot. I'm going to throw it a little bit off. And so that one's going to get bigger and bigger. And then my third rock, well, however far that went, I'm going to throw my third rock there, and so it's going to start to expand. Now, what can you tell me about the wavelengths now versus the wavelengths before? Or the wavelength on the right side?
Shorter than the one.
Since the speed of the wave is dependent upon the material, the water in this case, if the wavelength is smaller, remember the speed is frequency times wavelength, if the speed of the wave is staying the same, because that depends upon the medium, the water or the string or the air, if wavelength goes down, frequency goes up. speed stays the same. So on this side of it, you got a greater frequency. If you're a bug on the water, you're going to hit the waves more frequently. And on this side of it, there's a lower frequency. The wavelength got bigger, frequency got smaller. So here, wavelength goes down, frequency goes up. And on the back side, wavelength goes up, frequency goes down. I'm willing to bet most of you have experienced this in a slightly different form, because the same holds true for any wave, especially sound. As an object that's making noise comes towards you, the wavelengths get crammed together as it comes towards you. And as it goes away from you, so if you're on this side, as it's going away from you, the frequency drops. So when a car goes by you, that's why you hear the it's a higher frequency coming towards you, it's a lower frequency going away from you. Or an electric car, this is the Doppler effect. So if instead of thinking of ripples on a pond, we just dealt with these are pressure waves, this is sound, so it's one pressure wave after another. High pressure would be where I'm drawing the lines, low pressure is on the other side, is basically in the middle. Questions here? I'm going to do one more setup. So now I'm going to take my rock, I'm going to throw it into the pond, and that ripple gets bigger and bigger and bigger. I throw my second rock. This time I'm going to throw it outside the ripple. The third rock, I'm going to throw outside that ripple. So what's happening here where I've got two waves stacked on top of each other? These are two peaks, two high pressures on top of each other. What happens when waves meet?
Don't they bounce off of each other?
Not bounce off each other. I know it sort of appeared that way, but they actually passed through each other when we were doing the hallway. In the hallway, Riley and I sent waves towards each other. What happens when they met?
They meet down.
It created what?
That's what they cancel out.
If they were opposite sides, they would cancel out.
They created a down, right in the middle.
It didn't go down in the middle.
They created a bigger,
Yeah, got a bigger wave. If they're on the same side, you get a bigger wave. Constructive interference. This would be destructive interference when they met. That would flatten out. So when I've got the high pressure here on top of high pressure, I've got even higher pressure. I've got constructive interference. Now, if this thing making noise, I have it set here. I throw a rock and then I throw a second rock. Maybe a period of a second at best. But if I'm doing 440 of them every second, or 607, which was the last one I did. This is the speaker vibrating 607 times a second. Then that's a lot of waves that are stacked up on top of each other. So we end up with we basically get this cone here. Not great drawing, but we get a cone here of all these pressure waves that are building up on top of each other. And so it sounds incredibly loud. And the name for this? That's a sonic boom. So if you have something that's making noise, which is going to be pretty much anything, that's traveling faster than the speed of sound, It's gonna build pressure wave upon pressure wave, and ultimately, it sounds incredibly loud. If you've ever been to an air show, potentially you've heard it, or you've been around when some hotshot pilot decides to fly faster than the speed of sound over land, which is illegal. There's one more thing I was gonna say about it, but it's lost. So if I took a long string that thin as it went, because remember the speed of the wave is the square root of the tension over the linear density, which is just mass over length. So if I look at a section right here, it's got a certain mass to it. If I take the same length, but it's skinnier rope, I have less mass. So if I took a wave and I took this tapering string and I went up and down on it, and I created a pulse. As the pulse went down, my linear density gets smaller, which means my speed gets faster. My speed will keep going. Now, if I happen to have a free end down here, when the wave gets to it, basically, it's going to be in this position, then it very quickly drops down to that side on the free end. When it does that, the speed of that tip will be twice the speed of the wave. So if I could get a wave running on this thing so that it's traveling at, we'll just say more than 170 meters per second by the time it gets to here, then I can get that tip to travel faster than the speed of sound. It is a sonic boom. It is also a whip cracking. And so, I used to have them in my office so I could do demos with them, and this one probably works better than